So, welcome back to lectures on engineering mathematics 2, and this is module number 1 vector calculus and the lecture number 6 on Green's theorem. So, today we will discuss Green's theorem. Basically, this theorem tells about the transformation between double integrals and line integrals. So, in the last lecture we have already discussed what are the line integrals or the curve integrals. So, coming back to the theorem, let us just go through the statement. Let this R be a region. So, here we have R a region in R2. So, we are talking about the two dimensional plane now, whose boundary is a simple closed curve. So, we have a region R in R2 and whose boundary is a simple closed curve. That means, the curve does not intersect itself. So, we have already discussed in the last lecture. So, which is piecewise smooth, that term is also discussed already. The another thing here is oriented counterclockwise, that means when we traverse on this curve. So, for instance, we are traversing in this direction, then the region R always lies left to the tracing direction. So, if we are tracing in this direction, then this region is always towards the left. So, this is what we call the positive orientation, or the here the oriented counterclockwise. Okay. So, then if we assume that this f is a vector here f1 x y, f2 x y on two components, we are talking about the two dimensions now, and be a smooth vector field. That means, the f1 and f2, these two functions of two variables are C1 functions. So, they are continuous and differentiable on both the region R and as well as on the boundary. Then what we have this interesting result, that this curve integral C f dot dr, or we can define this curve integral with this f1 dx plus f2 dy. If we write this in component wise. So, this curve integral is equal to this double integral. So, this double integral is taken over this domain R, and we have here these two partial derivatives, the partial derivative of f2 with respect to x and minus this partial derivative f1 with respect to y, and this difference, and we are integrating over this region R. So, this curve integral is transformed to this area integral, the integral over the domain R. And just to be noted that this integral can also be written as, so here we have the curve integral, the right hand side part which was written here in component wise, that the partial derivative of f2 with respect to x minus partial derivative f1 with respect to y, and this integral over we can also replace by dA or dx dy. It is a double integral over this R. So, this integral we can also rewrite in this curl f and the dot product with the k, because if you recall that the curl f is nothing but the determinant of del over del x, del over del y and del over del z, and then we have from f, let us say f1, f2, and the third component is anyway 0 here. So, if we just get this corresponding to this kth component, because here we are doing this dot product with the k. So, we do not need the other I j, they will be anyway 0, the component sitting with I and j will be anyway 0. So, this with the k here, what we get, del over del x of this f2 minus this del over del y of f1. So, this is, and when we have the dot product with this k, then we will get just this difference which was mentioned here in the theorem. So, either we write in this component form or we write in this curl f dot k form, because this form will be used later on for generalization to the higher dimensions. So, at that time we will discuss this form again. Okay, coming back to the proof. So, a simple idea of the proof is, So, we consider that this C is a simple smooth closed curve in this x y plane, and with the property that the lines parallel to the axis, so parallel to the x axis and the parallel to the y axis cut no more than 2 points. So, this is what the restriction we have on the curve. So, this is the closed curve, we have considered a simple smooth closed curve, and if we draw these line parallel to the x axis, or we draw the line parallel to the y axis, in both the ways the lines will cut not more than 2 times this graph. For example, if we draw this, so it is cutting 2 times, or we draw in this direction, again it will cut not more than 2 times. So, and then we break this curve into the following 2 curves. So, here these 2 lines. So, this is the whole curve lies between these 2 lines, x is equal to a and x is equal to b, and what we are doing now, we assume the C1, which is y is equal to g1 x, that is the curve here. This curve from x is equal to a to this x is equal to b, this is denoted by y is equal to g1 x and the C1. The another curve which starts from this end point here and goes along this up to this b point, that is what we are calling the C2, and let us assume that the equation of the C2 is given by y is equal to g2 x. So, here for g2 x we have this x which is which lies between this b and a. So, here we have this x which varies from b to a. So, that is exactly given here. Now, the curve C, the given closed curve, simple closed curve C is the union of the two, because this the entire smooth closed curve was divided into 2 portions, one was C1, the other one was C2. So, now what we do here, we integrate del f1 over del y, that was a part in this result when we have this curve integral to the double integral. So, we integrate this del f1 over del y with respect to y from this g1 x to g2 x. So, we are doing this in the direction of y, and the limits will be from this curve to this curve. So, from this g1 x to the g2 x, we are integrating this del f1 over del y with respect to y. So, since we have this derivative and then we are also integrating with respect to y. So, this is simply f1, and then we have to put the limits from g1 to g2. And then we have this f1, the y is replaced with the g2 x, and here the y is replaced with g1 x. So, this is the result we have just by integrating del f1 over del y with respect to y. Now, we integrate with respect to x from a to b. So, in the direction of y we have integrated already from this boundary to the upper boundary, and now in the direction of x we have the maximum range here from x a to b. So, basically we are integrating over the whole given region R. So, that is the result. Now, here a to b over x, and then this was the already we have computed. So, this was f1 x g2 x and f1 x g1 x. So, this is integrated over a to b, and here also we have the integral over a to b for x. So, if we just change the limit here, so with the minus sign, so then b to a, and we have f1, and just note that this y component is g2 x. So, which was if we look at the figure now, so this g2 x. So, here we are in g2 x, which varies from b. So, this was x is equal to b, and then we are going in this direction up to x is equal to a, and the y is replaced already with g2 x. That means, we are integrating over this curve C2. So, this is the integral over the curve C2, and similarly here if we note this y here is replaced with this g1 x. So, here we are integrating over the C1 curve. So, this is the integral over C2 and this is the integral over C1 curve. So, then we can combine the two. So, that means this C2 f1 dx and this is C1 f1 dx. So, with minus sign if we take common, that means this plus this. So, we are integrating over the curve this f1 with respect to x. So, this is the result of this area integral. This is the integral over this whole region R, and the result is this minus C f1 dx. And there was another term del f2 over del x. So, now we will repeat this. So, the first we got here this result, that the curve integral f1 dx, this minus sign also we have taken to the left hand side. So, the area integral this over R of del f1 over del y. Now, the similar steps we will repeat for del f2 over del x, and first we will integrate with respect to x and then with respect to y. So, now this time we will consider the same figure, but now we will fix in the direction of y these limits as c to d, and then we have these two curves h1y and this h2y. So, here we have this h1y and then here we have this h2y, x is equal to h2y. So, the C1 prime curve is the x is equal to h1 and this is our C1 curve. So, here y varies between c and d. So, y is bigger than c and less than d, and similarly here y again is between c and d for the C2 curve as well, but here it goes from c to and then d, the other was d to c. Okay, well, so now we integrate this partial derivative of f2 with respect to x and then with respect to y. So, here we have del f2 over del x and we are integrating over with respect to x. So, here we have the f2 now, and the upper limit is h2 and then the lower limit for x is h1y. So, again the similar situation. So, we will integrate now with respect to y from c to d. So, if we integrate from c to d this expression from c to d, so we will get the f2 where we have h2x and here we have h1x. So, if we consider this one, that this f2 and we have already this x1 is replaced by h2x. So, just consider this one, the x component is replaced by h2y. So, this is y and this is also y, because this was y here, this was also y. So, this is replaced by h2y, that means we are on this curve moving from c to d and then along this curve c2 prime, and here we have the other situation that this first component, this x is replaced with this h1y and then we are integrating over this y from c to d. So, we can also now change here plus and then d to c. So, we have c to d and then for the C2 curve, for the C1 curve we have d to c. That means, we have a closed curve now from c to d and then d to c on this curve C1 and C2. So, these two integrals will again make the whole closed curve where the f2 is integrated with respect to y. So, here we have this conclusion that the curve integral of this f2 dy is equal to this area integral of this del f2 over del x, and now we combine this result and what we obtained in the previous slide. So, we have these two results, the f2 with respect to y, then we have this area integral, the partial derivative of f2 with respect to x, and here it was the other way around. So, the f1 dx, this curve integral is equal to this area integral of this f1 with respect to y dy. And now we can add the two. So, we have this f1 dx, f2 dx, that is a curve integral, this f dot dr, and here the right hand side is del f2 over del x minus this del f1 over del y integrated over the given region R. So, this is the Green's theorem, the statement of this Green's theorem, the conclusion. that this curve integral, which was also can be written as f dot dr. So, this closed integral, the curve integral f dot dr is equal to the area integral, and this area is nothing but the enclosed by this curve C. So, this is the area R. So, we can instead of integrating over the curve, this theorem says that you can also it is equivalent to integrate over this region R, but then the integrand will change, which is del f 2 over del x minus del f 1 over del y. Okay, so, we will go through some problems here. One, verify the Green's theorem for this vector field, where the vector field is given by x minus y and the second component is x. So, the region R here is given, which is bounded by this cos t sin t. So, which is a circle, because t varies from 0 to 2 pi, it is a whole closed circle which is given by this parametric equation. So, we want to verify the Green's theorem, that means first we will compute the area integral or the line integral, and then the other one, and see the both the values are same. So, here the f 1, the first component of this f is x minus y, that means the del f 1 over del y, because in the Green's theorem we need to compute del f 1 over del y and del f 2 over del x. So, del f 1 over del y, since minus y is there, we have minus 1, and f 2 here is x, this is f 2. So, del f 2 over del x is 1. So, if we go first with the area integral, where the integrand was this partial derivative with respect to x minus this partial derivative of f 1 with respect to y. So, what we have here 1 and then minus minus 1. So, we have 2 times and this dx dy over this region R. So, we have the circle there, the of unit radius centered at 0. So, this was the circle, and the area of the circle we know, because the radius is just the one unit here. So, the pi r square, that means the pi. So, here this is 2 pi, the value of this area integral, the double integral is 2 pi. And now, we can evaluate this f dot dr, which we have already learned in the previous lecture. So, here the f, this was x minus y. So, x is cos theta, this is y sin theta, and then here again we have this x, which is not theta, sorry, it is a t. So, the cos t, and then dr over dt. So, we have this r there, and we can get this dr over dt as so, cos will be minus sin t and then plus this cos t and j. So, this is minus sin t and this cos t j. So, this is dr over dt. So, we have f when we substituted already this parametric form dot dr dt and then integrating over dt. So, this dot product will be minus sin t cos t, and then here the plus sin square t, and this will be cos square t. So, minus cos t sin square t cos square t, and this is 1. So, the 1 when we integrate, this is 2 pi and then minus half. So, 2 sin t cos t, here we can divide by half and multiply by 2. So, this 2 sin t cos t will be sin 2 t, and this 1 is integrated and we got this 2 pi, and then we have minus sin there. So, sin 2 t, which again will give cos 2 t and then upper limit lower limit, that will become 0. So, we have just the answer here 2 pi. So, this was the curve integral, which gives us this value 2 pi. Here it was the area integral, which gives us the value 2 pi. Sometimes this theorem is very useful, because very often we will observe now that this curve integral is easier for some problems, whereas the area integral is easier for the other problems. So, accordingly we can either perform this curve integral or the double integral to get the area of the to get this such integral. Now, another problem. So, we will evaluate this integral, this is the line integral using Green's theorem, and the C is a square cut from the first quadrant by the line x is equal to 1 and y is equal to 1. So, we have x axis, we have y axis, this is line x is equal to 1 and y is equal to 1, let us say. So, this over this we are this region, and then we have this curve, the boundary of this square. So, we want to get this curve integral. If we perform over these curves, so we have the 4 lines there, and we have to perform this integral. So, naturally that will have these integrals 4 times, which may not be very convenient. So, what we will do, we will use this Green's theorem and apply on this region R. So, the Green's theorem says that this will be equal. So, here we have f2 because it is f1 dx plus f2 dy. So, this is f1 with the minus sign, and this Green's theorem says that this will be equal to this area integral, which we can easily evaluate these partial derivatives. So, f2 with respect to x, that means y we will get, and f1 with respect to y we will get 2y, and then with the minus sign there also we have minus sign, that will become plus. So, we have y plus 2y integrated over this area, this region R, where the limits are 0 to 1 and 0 to 1, it is a square, and this is very easy now to compute. We have here 3y, that means 3y square by 2, and then upper limit is 1, the lower is 0. So, we will get just 1 from there. So, we have 3 by 2, the 3, this is 3y square by 2, and then we have limit 0 to 1, the other one will be also just 1. So, here we have 3 by 2 the answer. So, if we do this curve integral, for instance, over these 4 curves, 4 lines, then naturally it will not be as simple as we have computed this double integral. Well, so another problem where we will evaluate, or we will show that the area of this bounded by a simple closed curve. So, if we have a simple closed curve, and we will show that this area of any simple closed curve C can be computed by this integral, which is integral x dy minus y dx, and this factor half. Okay, so, the Green's theorem says that this line integral, where we will take this f2 and this will be f1 with minus sign, that is half is already there. So, the half we have taken, and then this is the Green's theorem, that f2 with respect to x, f1 with respect to y, dx dy. So, half, and then f2 with respect to x, that is 1, and then f1 with respect to y, that will be minus 1, but minus was there. So, minus 1 we will have plus there. So, this is just the dx dy over this region R, and this is nothing but the area of this region covered or enclosed by the simple closed curve C. So, this is the area of R. So, this is what we want to prove, that this area can be computed with this integral, which is half the closed integral over C x dy minus y dx. So, the area can be computed by this line integral, which we will see in the next example, just to demonstrate this, that using Green's theorem, find the area of the ellipse x is equal to a cos theta, y is equal to b sin theta. So, here the solution using this Green's theorem, what we have, the area of the ellipse, the previous example we have seen that the area can be computed with this integral half the closed integral over the C, where in this case we have this ellipse. So, that is our C here. So, we will do this integral x dy, and then we have minus y dx. So, let us just do this line integral directly. We have already this x is equal to a cos theta, y is equal to b sin theta. So, x is a cos theta, and then dy we can have from here, that dy is b cos theta and d theta, b cos theta d theta, then we have minus y, y is b sin theta, and dx. So, dx from this we will get a sin theta with the minus sign, and then d theta. So, minus a sin theta d theta. So, this integral we can perform. Here the a b we can take common, we have cos square theta, and then we have plus sin square theta. So, a b, and the value here, then a b and the 2 pi, but half will cancel out that 2. So, we will get pi a b, which is a standard result, that the area of this ellipse x is equal to a cos theta and y is equal to b sin theta is nothing but the pi a b. So, now we will evaluate this curve integral, where c is the boundary given by this x 0 to 1, and then this is y between 2 x square minus and 2 x. So, we have the situation here. So, we are talking about this area enclosed by this 2 x square is equal to y, and then y is equal to 2 x. This is the line, y is equal to 2 x, and the area between these two what we want to covered by this boundary, where this curve integral is taking place. So, using the Green's theorem, this curve integral we can convert into the area integral with these partial the difference of these derivatives, and then we can easily see that del f 2. So, this is your f 2 is 2 x y with respect to x. So, we will get 2 y here, and from here we will get this f 1 y, which is coming as 2 y. So, we have 2 y and minus 2 y dx dy, and this cancel out. So, we have the 0. So, this curve integral, this closed line integral is 0. But one thing just to recall, that this vector field here x square plus y square I and 2 x j can be written as the gradient of this scalar function, and that means which we have already studied, this is the conservative vector field. So, one should also note that if the vector field is conservative, then along any closed path, this was one of the closed path we have considered here, but we can take any other closed path also, and that value will be 0, because that is a standard result which we have studied before. So, here this is what exactly happening, because this is the conservative vector field and we are integrating over this closed curve. So, naturally this will be 0. Just a short note before we end this lecture. So, let us consider this vector field here, which is given by this expression, and the area is given by this inner part of this disk here, x square plus y square, bounded by this 1. Okay. So, we can parameterize this circle there by x is equal to cos theta, y is equal to sin theta, and we can write down this curve in terms of the theta cos theta I plus sin theta j is a vector function of single variable, and then we can compute dr over d theta, because in the curve integral we need to compute this. So, we will have minus sin theta, and there we will have cos theta. So, f dot dr we can compute. So, here we will substitute the x cos theta y sin theta. So, y sin theta with the minus sign, and x square plus y square will become 1, and then we have the dot product. So, this first component minus sin theta will be there, then here we have second component. When we substitute the sin theta cos theta, we will get x is equal to cos theta, and then this cos theta will be from the dr over d theta. Okay. So, this is the integral which we can perform, the value will be 2 pi. On the other hand, where if we compute this area integral using this Green's theorem, then we have the partial derivative of this f 2 and then partial derivative of this f 1, which are given in the problem. And if we do so, we can do this partial in differentiation, and then we will observe that this is coming to be 0, because here we will get minus x square plus y square, whereas here we will get x square and then minus y square. So, this will cancel out and we will get this value 0. So, here we got this value 2 pi, and for this area integral we got the value 0. So, what is the problem? Why this Green's theorem is not applicable? Why these two values are not same in this case? The reason is obvious, because if you consider again this R, which is bounded by this circle, and if we take a close look here, it is written that x square plus y square is greater than 0. So, 0 here is not the part of the region R. This is the region R, but this except 0. So, we are not covering the whole region covered by this simple closed curve, which is defined by this cos theta sin theta, this circle. So, the Green's theorem says that we have to integrate over the region R, which is enclosed by the closed curve. So, here this one point is not in the domain, because this was indeed not defined at this 0 0. So, therefore, this was not a part of the domain, and therefore, this is not applicable. So, it does not contradict the Green's theorem, but simply that Green's theorem is not applicable because the 0 is not a part of the domain. Okay, so these are the references we have used for preparing this lecture, and just to conclude, we have learned this Green's theorem, which says that the curve integral can be written as the area integral, and the most important here is that you have the curve here, let us say C, then this is the whole region R without leaving any point there, then this is applicable. This curve integral can be computed with the help of this double integral, or the other way around. If curve integral is easier, we can find such area integral with the help of the curve integral. Another important point which will be used in next lectures, that this curve integral can be also written as in form of the curl f and the dot product with the k, and this k was the perpendicular to our xy plane. So, we had the xy plane where we are working now here on 2-dimensional plane, and the direction of this k was perpendicular to this domain given here in the xy plane. So, if we do this dot product with the perpendicular to this plane, then we get exactly the integrand of this area integral. Okay, so that is all for this lecture, and thank you very much for your attention.